Now this relationship between the wavelength and the frequency is the main point of what we want to do today. That's where we're going. Question real quick, just to see if we're on the bus. I have a transverse wave that is moving to your right. And we took a snapshot of it and froze time right at noon. Now on that, this happens to be traveling on a string. On that string, I tied two pieces of ribbon at A and at B. And remember, this wave is moving to the right. I took a picture at noon, and that's what it looks like. If instead of a picture, I had taken a movie, we would see that those pieces of yarn at A and B would be moving. Right at noon, they would be moving. Now the question is, how are they moving? Is A going up and B down, or is A going down and B up? Are they both going down, both going up, or is A going to the left and B going to the right? With your clicker, how would they be moving if this were a movie? People, when you get older, get a job that you just love to do. It makes life so beautiful. I'm the happiest man on the planet. Okay, time's up. Okay. If this were a democracy, B would be the correct answer. Physics is not a democracy. Okay? Let's solve it. This is a transverse wave that is moving to the right. What that means is that as the wave moves to the right, the individual pieces of the string making up the wave have to move perpendicular to the wave. The wave's moving to the right, so these things have to move either up or down. That means E is, well, it's sick and wrong. Sick and wrong. If you chose E, think that through. Okay? Now, we want to look at the movie. We don't want to be stuck with this snapshot. So we look at the movie. And if we look at the movie, what we see in the next frame, this was the frame that was taken at noon. This is the frame that was taken right after noon. 1/10 of a second after noon. Okay? Because the wave's moving to the right. Now these pieces of yarn can only move up or down. And the yarn has to stay on the string. So that means this point A, where I've tied the yarn, has to move up there. And B has to move down there. So A will move up, B will move down, and the answer is A. Okay? If you got B, you need to reassess your life choices. Okay? Now, remember, it's all about pieces of the string getting out of the way for the pulse as it comes by. As this pulse, which is a trough, goes by, B has to move further away to let it, because it's the hump hasn't reached there, so it has to get further away from equilibrium. Whereas at A, the hump's already gone past, so it's going back towards equilibrium. Does that make it more reasonable?
If you just look at what's in front of the point, it'll show you which direction it's going to go.
Right. Exactly. So, in other words, this is right in front of that point, so it has to go there, because it's all moving that way. Okay, problem with your clicker. If the speed of a wave on a spring remains constant, but the wavelength is somehow decreased, what's that going to do to the period? Now we're getting to this relationship that we were talking about. Is that going to make the period increase, decrease, or stay the same? assuming the speed of the wave stays the same, making the wavelength smaller is going to do what to the period? Okay, get it done. Okay, decrease is the correct answer. These people are fun. Okay. Again, if we use this analogy of the train, it becomes clear what the correct answer is. Both of these trains are moving the same speed, let's say 40 miles an hour. They each represent a wave. The length of the boxcars represents the wavelength. If you're standing between these two trains as they go past you, the period is how long it takes for one boxcar to go past you. And if these boxcars are shorter, and they're both trains are going the same speed, these will get past you quicker. So that means the period is going to decrease. It's going to decrease, and the answer is B. Make sense? Good. Now, here's the guts of it. In 205, there was one equation to rule them all, and in the darkness bind them. It was Newton's second law. When we're dealing with waves, it doesn't matter whether it's moving waves, standing waves, longitudinal waves, transverse waves. We're going to find that all waves satisfy what's called the wave equation. And we're going to derive it very easily right here. We see waves that are rolling onto the beach, and we estimate the wavelength at about 3 meters. You measure the time between wave crests at 0.5 seconds. What is the speed of the waves? Now, you've all played this game. You're standing in the waves up to about here, and when the waves come, you jump up on your toes so that you don't drown. And then you go and you wait for the next wave, and you jump up on your toes so you don't drown. Okay, so you're at B, and the waves are moving to the right. So you just jumped up, and then the crest at A moves over and reaches you at B. How long is it going to take to get to you? Oh, we're told that's half a second. Okay? How far did it have to travel in that half second? Oh, 3 meters. So how fast is it going? That's not rocket science. It's going 3 meters in half a second. Well, that's 6 meters per second. What we just did is we took the wavelength and we divided by the period. Now, folks, that's not the form of the equation that I want you to write down. That's not the form that typically is used. Typically, we use the fact that the frequency is 1 over the period, and so we write the wave equation as the speed of the wave is equal to the wavelength times the frequency. And I'm going to put that up here as the grand high wave equation. Before the semester started, we were in Mazatlan, and I went out into the waves. My wife and my sister-in-law and brother-in-law didn't want to go because it was cold. And I was out there and just having a grand old time. Couldn't see anything because there was a lot of sand being churned up. And all of a sudden, there was just things bumping into my legs. You know, and I just, whoa, just all sorts of things bumping into my legs. And I quickly got out of the water, and as I'm getting out, there's these guys putting up these flags, and the flags are yellow, and when we ask someone about the flags, it says, oh, there's manta rays out there. Manta rays. It's exciting.